Good evening. Well, guys, we made it. It's the last Watson lecture of the 2024-2025 season. And I just want to thank all of you that have been here on this journey with us, and especially to thank the Friends of Beckman Auditorium, who have been supporting performing arts and this program since 1967. If this is your first Watson lecture, welcome. I'm Crystal Dilworth. I'm a neuroscientist, a science communicator, a Caltech alum, and your enthusiastic host of this program. Thank you, thank you, thank you. The Watson Lectures were conceived as a way to bring campus and community together in curiosity, in admiration, and in appreciation for the insights and the innovations that were developed here at the California Institute of Technology. And I think the founder, Ernest C. Watson, would be pretty proud of us. This is the 103rd year of the series, so that's awesome. And this year, we sold out. We invited and welcomed over 4,000 of you to Beckman Auditorium, over 7 lectures. Yeah. And we were able to address really relevant topics. We talked about debris flow after catastrophic wildfire, and we talked about how emerging technologies can be used to benefit extractive industry practices, and to assist global response to pandemic. And next year, we're going to do even more. So take a look at what we've got in store for you in the coming season. See some of your favorite topics on the screen. And then you can use the QR code to make sure that you register and give yourselves a reminder so that you come back, and I see you all in October. All right, but tonight, appropriately, we have chosen space as our final frontier. Gets better. Tonight we have the privilege of hearing from Tracy Drain. Thank you. Who apparently needs no introduction, but she is the chief engineer of NASA's Europa Clipper mission. Yes, thank you, come on. And she is going to share with us the spirit of adventure and opportunity that's currently being experienced by her intrepid team of curious scientists and engineers as they follow the Clipper spacecraft's sojourn to Jupiter's moon, Europa. First, before you hear from Tracy, you're going to hear an introduction from NASA's Jet Propulsion Laboratory director. You're going to see a short video about her life and work. And then after her talk is when you all get to ask your questions. So what will happen is a QR code will appear on the screen. You can use your phones to access Slido. That's how you can upload your questions for the speaker. If you don't like to do it that way, totally fine. Flag down one of our friendly ushers. They'll have a card. You can write your question down on the card, and they will make sure that it gets uploaded so that I can see the questions, and we'll get through as many as we can. I suspect there will be a lot, so we will do our best. Luckily, you can also hopefully catch her for a coffee outside in the front. If you're lucky, you'll see her there as well. All right. I think that's everything. You have persevered through my introduction. So please silence your phones, your watches, all of your tech that beeps, note your nearest exit, and help me welcome to the stage the director of NASA's Jet Propulsion Laboratory, Dr. Lori Usert.
Awesome. I love all those mission references, Crystal. Thumbs up to you. Points for you. Good evening, everyone. Hello. Where are my JPLers at? All right, all right. Well, you and all the rest of you are in for a huge, huge treat tonight. I'm so honored to be here to introduce one of our most amazing technical leaders at JPL, Tracy Drain. Yeah, you already gave it up for her once. You're going to give it up for her a bunch more times before this night is over, and she's earned every one of them. She has worked at JPL for more than 20 years, and she's contributed to some of our most ambitious missions. And I am personally very excited that I get to hear her talk about one of, well, okay, so here's a little secret. We're not allowed to have favorite missions. As the JPL director, you're not allowed to have a favorite mission. I get asked all the time, what's your favorite mission? I don't have a favorite mission. They're all perfect. One of my very favorite missions, Europa Clipper, which of course is currently on its way to investigate a fascinating world, an ocean world, an icy moon of Jupiter called Europa. And if you'll indulge me, this evening marks a milestone for me personally. This is my final public event as the director of JPL. Thank you. I'm concluding my service at the end of this week, and I honestly can't think of a more appropriate person to be able to introduce tonight or a more exciting topic to get to discuss at this event, because these missions like Europa Clipper, are hard. They take decades to conceive, design, engineer, build, test, launch. Launch on this one was especially exciting. There was a hurricane in the middle of it. I don't know if Tracy's going to talk about that. Hurricane? Yeah, okay, good. You got some hurricane. I was in the hurricane, so it was very exciting. You know, build, launch, fly. Jupiter's far away. It takes almost 6 years for us to get there, 1.8 billion mile journey our Europa Clipper is on right now. And only after all of that, by the way, successfully inserted into orbit around Jupiter, only after that do we get to the science. Do we get to that stuff, the reason that we're going. And it's for this reason, it's how hard they are, that I call them modern cathedrals. They are generational quests that take us on extraordinary journeys, and you're going to get to come along with us on that journey tonight. And those journeys don't just happen. They happen because of something that I call magic teams. If you've been on a magic team, you know what I'm talking about already. A magic team is a team that looks challenges and obstacles right in the face and knocks them down, each and every one, until you get to launch or until you get to science. Not only that, it's a team that makes that journey full of those challenges extraordinary. And magic teams don't just happen. They happen because of incredible leaders. They take a level of collaboration and teamwork that energizes everyone. It takes people who bring the best of themselves every day and bring out the best in others. And Tracy Drain is one of those leaders of our magic teams at JPL. She is the kind of leader who not only brings incredibly deep technical expertise and excellence, but also has an incredible infectious sense of passion, of dedication, of curiosity. Got you there, Rover. That helps us imagine how we can achieve together what no one of us can achieve alone. And you really need people like Tracy who bring the magic for a mission as tough as Europa Clipper. As I already said, it's traveling 1.8 billion miles on a very complex flight path. Once it gets to Jupiter, every time it flies by Europa, it gets like 1 million chest x-rays worth of radiation. It's a nasty environment out there. So to build this spacecraft that can withstand that horrendous environment is worth it because of the incredible science we get to do with it. And the science that's enabled by extraordinary technical leaders like Tracy and like the rest of the Europa Clipper team, I know a lot of whom are here tonight. So you're going to get to see a video that talks more about Tracy in just a second. But I just want to say, extraordinary technical talent, incredible leader of people, and passionate speaker, advocate for the work that we do. Tracy Drain is the whole package. Enjoy hearing a little bit more about her in this video, and enjoy the evening. Thank you all for coming.
I grew up in Louisville, Kentucky, and really loved going outside and digging around in my grandmother's backyard and playing with the bugs. I was very exploratory, but also super nerdy kid. My mom was just always very interested in the world around us. She always indulged my interests in little things. I loved rocks. I would collect rocks around the neighborhood. Some parents might go, great, a rock. But my mom was like, ooh, tell me about your rock. She was just always encouraging me, where I would go like, Mom, come into the closet with me. And we shut the door and I'd strike this flintstone. And she's like, oh, that's really cool. You can smell it so far. And I'm surprised that she didn't say, you know, you're gonna burn the house down. Like, get out of the closet. There's clothes in here. Like, go do it out in the backyard at night. Maybe she did say that, but she would go hang out with me in the closet anytime and like play with flintstones. It's very cool. My name is Tracy Drain, and I am currently the Chief Engineer for the Europa Clipper mission. Mom bought books called Childcrafts, and they were like a series that went along with our printed Encyclopedia Britannica. And I remember reading the story in there about how scientists thought the solar system was formed, and just being really surprised that scientists could figure that out, something that happened over 4 billion years ago. And I'm like, you have to be kidding me. I thought it was the coolest thing. I was in band from the time I was in 6th grade all the way through a couple first years in college. There was something super magical about that I just adored. All the half notes and eighth notes and quarter notes and sixteenths and how they add together. I feel like one of the reasons I have an affinity for math is because I started playing music from such a young age. I think it was one of the best things I could have been doing with my time then. For whatever reason, I couldn't piece together what you do with an astronomy degree. So I chose to study engineering because I knew whoever was building things to go off and study space needed engineers of all kinds. And I chose mechanical because it felt very basic, very fundamental. You could do a whole bunch of things with mechanical engineering. At Georgia Tech, I had decided to go and get my master's degree. Ayanna Howard was an engineer who worked here and was with the recruiting team there, and literally reached out and stopped me and was like, hey, don't you want to talk to us? And I'm like, who are you guys? And I was very, very fortunate that she was gracious enough not to be like, you idiot, keep walking. I'm going to talk to the next person. For people who haven't visited the lab, it's this nice college campus feeling place with a bunch of different buildings, all relatively close together. Lots of people walk between them. You could just hear snippets of conversations of the things that people were working on, like how do we get a lander on this planet? How do we put an orbiter around this planet? How do we dig beneath the ice on this planet? You could just feel the energy of all this really awesome work that was going on. I'm very fortunate to have gotten a chance to work on different missions: Mars Reconnaissance Orbiter, Kepler, Juno, Psyche, and now the Europa Clipper mission. Where it gets interesting is different missions they have, the different places they're going to, the different science they're trying to gather. That gives us a lot of meat to chew on as systems engineers and other types of engineers to get a final design that ultimately works the way we want it to. I was able to meet William Shatner and Nichelle Nichols, who played Uhura, which is great because they meant a lot to my mother and to me when I was growing up. It was about showcasing how a lot of different kinds of people from a lot of different kinds of background can work together to get things done for the benefit of all. And I think that's just such a beautiful, beautiful undertone message throughout Star Trek that I love it. Hello, everyone. Thank you so much for coming out to hear the adventures of Europa Clipper. And wow, what beautiful introductions. Thank you so much to both of you. I want to take you with me everywhere to introduce me to all my things. So here we go. Let the adventure begin. As you heard, you're going to hear about a mission heading to a cool destination in the Jovian neighborhood. First, for those of you who are not familiar with Europa Clipper, it's one of the 4 large Galilean satellites that were discovered by Galileo back in 1610. Europa is the smallest one that you can see here, but it's still a little bit, it's the 6th largest moon in our solar system. A little bit smaller than our moon, about 2,000 miles in diameter, or roughly the distance from Los Angeles to Atlanta. One thing that I love about being an engineer on missions like this is it gives me an excuse to learn a little bit about the science. And so I got to learn from Bob Papalardo and our team what are the cool things about Europa Clipper. It's unusually smooth. There are very few craters on it. So that means it's geologically young. Something is happening to resurface the moon, which is a clue for why scientists believe there is water underneath the surface. There's many things that they want to learn about it. So Europa Clipper, the scientists believe, have a thick shell of ice, maybe 15 to 25 kilometers thick, and under that, lots and lots of water, more than 2 times the Earth's oceans combined, right? And for those of you who are aware that Europa Clipper is around Jupiter, you're thinking, but wait, it's cold out there. What gives? It is very cold, but scientists discovered the evidence for this ocean there using a magnetometer. Europa has what they call an induced magnetic field. Here on Earth, the water, as it moves around with the tides, the ocean, bends the Earth's magnetic field. And it's enough for you to measure. And that's because salty water is conductive. And so when Galileo was there studying Jupiter's magnetic field and found this induced magnetic field around Europa, that was an indication that there must be something there, perhaps briny water. But again, why water? It's really cold out there. How is there enough heat? Well, there's a thing called tidal flexing or tidal heating. Europa orbits around Jupiter in an orbit that's not exactly circular. And when you're closer to the moon, the gravity acts stronger. When you're farther away, it acts less strong. So every time it goes around Jupiter, once every 3.5 days, it's like being squeezed and released and squeezed and released. And that makes enough heat inside to melt an awful lot of water. So why do scientists care about the water? Well, that's because when we think about life here on Earth, water is always involved. There's lots of water on the Europa underneath the ice. It probably has lots of essential elements from the formation of the solar system and impacts from comets. Chemical energy, both from below with all that heat and above, and it's been simmering there for over 4 billion years. And we know that on the Earth, when you look way down below the ocean at the ocean's bottom, there are hydrothermal vents, heated water from heat inside the core. And even though it's too deep for sunlight to get down there, you end up with a very rich diversity of life. And scientists are wondering, are the conditions at Earth enough to sustain some kind of life? Don't know, but we're interested in studying lots of things about Europa, which will be pathways to finding out. So that's why scientists are excited about Europa and why we would send a mission like that there. For the mission overview, as you heard, we launched in October 2024, and we just completed a Mars flyby in March. Yay. We're going to do an Earth flyby, like loop back around, do an Earth flyby at the end of next year, and that will give us our final boost to get all the way out to Jupiter by 2030. So, you know, just wait for us. All good things are worth waiting for. And then we'll be doing multiple flybys around Europa in order to gather lots and lots of juicy science. Getting all the way out there and doing this kind of mission gives us lots of engineering challenges to solve. One of those challenges is just how far away we are going from the sun. So how much less light do you have out there? If you can imagine taking a balloon and blowing it up, it's stretching the plastic so that one little square, if you drew it on there and then blew the balloon up to twice its diameter, that square would be stretched to 2 times 2 or 4 times the area, the same plastic stretched across that, which means that the size square that you started with has 1/4 of the plastic. And if you blew up the balloon to 3 times, you get 1/9 in one single area, if you go up to 5 times, and so forth. So when you can think about the sun's light expanding, the farther you get away, the more it dissipates, the less light you have. Jupiter is 5 times farther away from the sun than the Earth is, and so it receives less than 1/25 of the light over a given area. It is really far away. And so if you want to have a solar-powered mission, you need to go big or go home. Europa Clipper is the largest spacecraft NASA has ever developed for a planetary mission. It is 30 meters or 100 feet from wingtip to wingtip, 5 meters tall, 15.6 feet. It will literally hang off the edges of a basketball court. Someone had the great idea that we should get a holographic projector and project a Juno on the basketball court here at the arena in LA. I really want that to happen. So if anyone's listening, venture capitalists, please do that for me. It weighs about 13,000 pounds when it's fully fueled, when it was fully fueled for launch, and about half of that is just fuel, and the rest is dry mass. Here are pictures of the solar arrays at Airbus before they were shipped to Cape Canaveral, and then at KSC getting checked out after installation on board the spacecraft. Another engineering challenge is just how far away we are going from the Earth. Earth is there, you can see the little dot. We're 1 astronomical unit away. Jupiter is 5 astronomical units away. Earth goes around the sun once every year. Jupiter takes much longer, almost 12 years to go around. And so sometimes we're 4 AU, sometimes, or 4.5, sometimes we're more like 6.5. So in order to deal with that long distance, we have a 10-foot high gain antenna that we can use. It sort of focuses the radio signal, almost like a laser pointer that you would use with your cat, pointing it directly at the Earth. And you can see some other telecom antennas on there for when we can't point the high gain at the Earth very specifically, but the high gain is the one that lets us get lots and lots of data down. The operations team just this past Friday, I think, got our first 1 megabit per second pass sending data back from where we are out beyond 2 AU right now. I know, woo, it's very cool, milestone for us. We'll be able to do about 500 kilobits per second all the way out at Jupiter to a single deep space antenna station here. And so that's the other part of the equation. You need large ground antennas to be collecting the data that the spacecraft is sending back. As the Earth rotates, your spacecraft is out in a single line, and you would love to have 1 station every 120 degrees around the Earth, so there's 1 in view all the time. But there's an ocean there, countries that we don't own, and so we have to kind of put them where as well as they can go, and they're almost 120 degrees apart. There's 1 in Madrid, Spain, a complex with lots of stations, 1 in Canberra, Australia, and 1 not too far from here in Goldstone, California. And they're quite large. This is what a 70-meter antenna would look like on a football court and a 34-meter that we use too. Nice big ears listening to us. Another engineering challenge is just the radiation environment at Jupiter. You heard Dr. Leshin mention what that is like. If you've ever thought very much about Jupiter, it's a giant ball of mostly hydrogen and helium, but it's so big that it has so much mass that it compresses enough under its own gravity that as you get deep inside, that hydrogen compresses into a liquid. And as you go further, the pressures and temperatures get high enough that the little electrons going around the atoms get squeezed off. They're free-flowing in there. That creates electricity. Jupiter rotates once on its axis once every 12 hours, and that generates a monstrous magnetic field. And then the high energy particles from the solar wind, and they get spewed out of Io, the volcanic moon of Jupiter. Those get trapped in the magnetic field lines, accelerated to near the speed of light, which means Jupiter has a giant donut of radiation around it, with Jupiter sitting in the donut hole. And just gratuitously, I couldn't help throwing this in. Juno, which is a mission that I got to work on, has been studying Jupiter's magnetic field, and someone used that data to put together this really cool 3D visualization of what its magnetic field looks like. Cool. So what do we do about that in terms of engineering challenges? Well, part of the solution is just the trajectory. It would be much harder if we were orbiting Europa, which is down inside that donut hole of radiation. And so what we do is put the spacecraft in orbit around Jupiter, and we spend most of our time way out of the radiation field. This little animation is Jupiter in the middle. The inner moon is Io, which is getting the most radiation. Europa is next, Ganymede, and then Callisto. And you can see in that second yellow ring where the spire graph gets very dense, that's Europa Clipper. So the Jupiter spacecraft, Clipper spacecraft will come in, fly by Europa, use that to set it up for its next pass. For the first part of tour, we will be doing that once every 21 days, and for the second half of the mission, roughly, we'll be doing it once every 14 days. So part of the solution to all that radiation, don't stay in there all the time. The second part of the solution is to have a electronics vault that we put our computer and other sensitive components inside. It's made of about 1/3 of an inch thick aluminum and knocks the radiation environment down inside there to something that the electronics can better handle. And there's spot shielding around the spacecraft. There's a smaller vault for some of our telecom components. And many components are selected because they are especially resistant to radiation. Remember that. That is a theme that we will come back to later in the mission, or later in the presentation. What are some of the cool science objectives? The scientists want to know more about the interior. How thick is that ice? How deep is the water? What is the interior of the moon like? They would like to understand the composition of the surface, some of the geology, all of the cracks that you see. What can they tell us about how the moon has behaved over time? And also activity. This is an image showing some potential plume activity there on the moon. And so our challenge as engineers is to figure out how to get instruments there in order to collect their data. And part of the solution, of course, is having a pretty fantastic instrument suite on board. We have things that are going to measure the atmospheric composition. There's a very tenuous atmosphere of molecules around the moon. We're going to look at the dust, measure more details about the magnetic fields, look at the plasma environment, and then look at the UV spectrum of the surface and the atmosphere in order to understand like what it's made of. There's camera that's going to be taking pictures of the landscape in 3D and color. Ethemis, bookmark that, we'll come back to that one too, which is a thermal imager looking for hot spots, which could be indications of where the ice is thinner. A chemical fingerprint analyzer, an IR infrared spectrometer, and also reason. You heard Dr. Leshin say that we're not supposed to have our favorite missions. We're probably not supposed to have our favorite instruments, but I gotta say, I think ice penetrating radar, super duper cool. So I'm a fan of that one. Don't tell any of the other scientists. Shh. Is this being recorded? No. So we're festooned with lots and lots of instruments to go and measure all sorts of fabulous things about the moon. So where are we now? We launched in October 2024, check. We did our flyby in Mars, and we're on our way. I'm sure you would like to know, how has it been going today? First, I'm going to tell you some how is it going to get up to that point story. Me personally, I joined this mission as the lead flight system engineer in summer of 2020, and you guys probably know what was going on in the world at that time. This was my battle station at my house, a standing desk with a bench. My cats really loved that I was home all the time, and I got to know my team of 35 systems engineers at that time before it grew to 45 later, all remotely, all online. And we had to work very creatively together, figuring out ways to find the problems, solve the problems, being very, very just interconnected through the magical technology that we have today. We worked remotely for about a year and a half, as you can see by the very dead plants there were when we finally got back there. So COVID was a challenge for us to overcome, figuring out how to work together that way in a very critical part of the mission. For those of you who are familiar with JPL design timelines, I joined about 6 months before our critical design review, and we did all of that, and then the next year leading into our system integration review all remotely. I'm going to tell you one of the things that we did as an adventure pre-launch, an example of something that isn't exactly hardware design related, but is what we call a trade. You're trying to solve a problem, get something done, and you have to figure out what are the knobs you have to turn, and what are the options you have, and what are the pros and cons. And for this one, for those of you who are laser focused on what our mission design looks like, we leave the Earth, we go out past Mars, we loop back into the Earth, and if you can see right over here, our blue orbit actually goes a little bit closer to the sun than the Earth does. And so the spacecraft can get pretty warm there. And then we go all the way out here to Jupiter where the spacecraft will get very cold. So we had to design a spacecraft that can handle super cold temperatures, but also not get too hot. And one of the ways that we can deal with that is when we're in the inner solar system, you keep your high gain antenna, our big 10-foot dish, point it at the sun, so that shades some of your spacecraft. You have to tilt your solar arrays so that they don't get too hot, because we discovered when they get too hot, it influences the voltage for our power control distribution assembly, and if it got too hot, it would get above where we tested it. But also, you can't tilt your solar arrays too much, because then those long, thin radars could get in the way of our star tracker, which is what the spacecraft use to figure out where it is. So this is one of those things where you're planning your wedding, and you know that person A cannot sit next to person B, but really needs to be at the table with person C. And if you don't get this right, like, everything is going to be disastrous. So ops trays are kind of like that. And it took a long time for us to figure out exactly how to make this work, but we came up with a great solution. And now that we're in flight and we're seeing the details of how our spacecraft is performing, we're just taking a closer look to figure out if we need to make any adjustments. Yay, ops trays. Oh, whatever, I had more pictures. So this is the long reason antenna I was talking about, and our star trackers that need to have a clear view to the stars so the spacecraft knows where it is. Some other pre-launch adventures we had were hardware related. This is our spacecraft all wrapped in its lovely thermal blanket so that it doesn't get too cold all the way out at Jupiter. And one of the really cool things about the spacecraft design is for our vaults, which is where our computers are. You guys know you put your laptop on your lap, it gets pretty warm. Computers get warm in space too. And so in order to use that heat and not just waste it, there are tubes full of fluid that are piped down around the prop tanks, which sit in here, and there are pumps to run them in order to use the waste heat to keep something warm so we don't have to use so much power. Very elegant. But the thing about that is your pumps have to work like all the time in order to keep that heat flow moving. And the team discovered, kind of late in the game, that there was a concern about lifetime, about wear out of the pumps. And we had two of them, because you have redundancy on missions like this. One stops working, you still have another one. But the life concern was such that we didn't think two was enough. And so we ended up adding a third pump. And for those of you who work on hardware, you know that adding a pump on a drawing, pretty easy, draw some lines, but you have to figure out where is this gonna go in the spacecraft. We have the tubes all laid out, we know where the pumps are supposed to go, we only have so much space. Like, it was kind of crazy. And it was very, very impressive to our team, who figured out how to ultimately make that work. So Europa Clipper, flying to Jupiter, 3 pumps, yay. You heard Dr. Leshin mention MOSFETs. Very horrifyingly late in the game, we discovered that these little transistors, which you need to have a certain voltage go across them to be considered open or closed on the spacecraft. And there are hundreds of these, 1,500 embedded in components all over the spacecraft. And we learned that these components we selected, because they're supposed to be able to deal with the harsh radiation environment, were not performing as well in testing that another mission was doing. And so after we stopped tearing our hair out, a heroic group of people went off to go dig deep and figure out what's going on here. And this was, deep into the last several months getting ready for launch. You can see the date on this. I cannot read it from here. Can you guys read that? July. When did we launch? October, right? Wait. So we're still dealing with this problem that late in the game. People had to go and figure out, okay, how can we understand what are we seeing in testing? What is different about the way we are going to fly the mission than what they're doing in their test environment? Is there something we can do about them? The team determined that you can heat up these parts, and that will kind of heal them from the radiation performance hit that they're getting and make them work back to the way they used to, and you can kind of ensure that their life goes the way that you want them to. But they're scattered all over the spacecraft in a whole bunch of different components that need to work, powered on and off at different times and be in different temperatures. So it was pretty hectic for a while for the team to be able to gather enough information and put the story together to ensure we would be able to launch the spacecraft on time, which is a little horrifying. The whole picture with the Earth and Jupiter and planets only line up so often for you to be able to get your spacecraft to where it needs to be. So very, very heroic effort by a lot of people to go do the work to figure out that we can successfully operate this mission. Another thing that was pretty magical about this is in the 3-month time span, they developed an entire hardware box that is full of a sampling of these transistors that we can put on board the spacecraft so that we can have it as our canary. We literally call it the canary box. So that as we are orbiting around Jupiter, we can pay attention to how it's behaving and let that inform us about what we should be expecting on the rest of the spacecraft. Crazy time. That was one of the scariest things, in my opinion. I still might have some nightmares about them. You heard about Hurricane Milton. So this mission was intended to launch on October 10th of last year. And everything, we were nervous about the transistors, the MOSFETs, there were a bunch of other things we were working. We got the spacecraft down to the Cape, endless number of issues that were going on. I would have to stand here for like 16 hours to try to tell you about even a fraction of them. And with all of that, we learned, some days out that there was a hurricane heading for Florida. And we're like, you have to be kidding. This is a joke, right? That's not a thing. But it was a thing. And the hurricane was heading that way. And as the forecast got closer and closer, we learned that it was essentially going to go right over the Cape. And so a lot of personnel were evacuated from the Cape, the vast majority of our Europa Clipper team. I think we left a couple of people there holding down the fort from our team. Lots of the scientists were down there in nearby hotels. And one of our extremely talented engineers, but also a fantastic artist, drew this picture in a few hours the night before the hurricane was supposed to hit. And we sent it down to our team to let them know that we were thinking of them and all holding them in our hearts and hoping that they would all be safe. And that Europa Clipper, that's actually the spacecraft with its little solar arrays folded up under the blanket. It's just dreaming of launch once the hurricane could get past. So yeah, the hurricane itself did go pretty much directly over the Cape. That blue insert square shows you kind of where Cape Canaveral is. Like it's like aiming, it's coming right for us. Right? And after the hurricane passed, then we were all holding our breath, waiting for the damage assessment and recovery team to check everything out on the center and make sure that there hadn't been damage done to the launch pad and there hadn't been damage done to the assembly facility and that the spacecraft was okay and everything was ready to go. So we ultimately were able to get to the launch pad and have the spacecraft launch on October 14th. Yay! Super. And, oh wait, there's more. So this is the kind of picture you're used to seeing about a launch day and everything was great and we're all happy and we high-fived and then we did the rest of the day and went home and took a nap. But there were some pretty incredible things that happened on launch day itself, kind of behind the scenes. So I could not resist putting in a handful of videos for you to see, if I can find my clicker. So this video is from 3 minutes and 18 seconds before liftoff. Oops. Nope. Un momento. Clickety click. Where is my mouse? There we go.
Yes, LD, this is NLM on countdown 1, NASA spacecraft, and the NASA team is go for launch pending resolution of the anomaly.
What?
Copy. Go pending outbrief of the issue being discussed on the anomaly net.
Affirmative.
Okay, Tim, so they've mentioned that they're working an anomaly. Tell me a little bit about it.
Yeah, so as we mentioned, they're monitoring some temperatures on the second stage, and things are the teams continue to look at that as they continue filling second stage with liquid oxygen.
Yeah, so you see the time, 2 minutes and 40 seconds, right? And so a bunch of, okay, I did not set the stage for you. So the way a team works around launch is you have a bunch of people who go down to the Cape and they're responsible for everything that happens to the spacecraft before liftoff. And also down there are the folks who built the rocket. We did not build the rocket. They built the rocket. And they're responsible for a lot of things, in the end of the countdown. I am the mission manager at this point with the team here at the mission support area in Pasadena. And we are responsible for anything that happens to the spacecraft after it launches and gets separated. And then it's our job to pay attention to it, monitor it, be ready to command it. And so at this point, there's nothing any of us can do. So we are in the mission support area. I'm locking eyes with the flight director, Pranay, and we're like, did you hear that? I heard that. Was it an anomaly? What's going on? Looking over at the launch phase lead, sure. And I was so impressed that the SpaceX folks who were talking about this on the anomaly, they stayed cool as a cucumber the entire time. They had words like, yes, we're working through our procedures, and we're like, procedures? Do we actually? Okay, fine. But ultimately, they worked through the problem. I can't remember exactly how close to launch we got, but like the hair was starting to light on my head. But they worked through the problem, and then we were cleared and ready to go. So here's actual liftoff.
T-minus 15 seconds and counting.
And here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition. And liftoff. Liftoff of Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Engine chamber pressures are nominal.
So happy about that. That was my 4th launch in the time that I've been at JPL. I left Psyche before launch, and it never gets less exciting. It just feels so good to have all your blood, sweat, and tears get off. It doesn't really get less stressful either, but it doesn't get less exciting, so that's great. And then, not long after liftoff, we got to see this.
Next thing up in about
lift.
10 seconds will be fairing separation.
NYPY FTS has saved.
And the fairing has protected Europa Clipper on its ascent up into space, but once we get into space, we don't need that fairing anymore.
there they go.
Confirmed.
Yay!
Fairing is
There it
separated,
is.
and those will be recovered, Daryl, by SpaceX's own recovery ship, Go Cosmos.
Yeah, and crazily enough, right, you would think that all of us who are inside on the mission know everything about everything that there is to know. I either didn't know or forgot that there was going to be a camera right there. And when we got to see the actual little baby spacecraft with its solar arrays all tucked up inside the fairing, I'm like, no way! Like, that was so cool. Arissa, why didn't you tell me? It's the best. And then you can see the timestamp on that. That was just a little bit less than 5 minutes after launch. And it took an hour for the spacecraft to get all the way, for the launch vehicle to get all the way through ascent and all the things it had to do before we actually separated from the launch vehicle.
Europa Clipper, separation confirmed.
Yay.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight, Mick.
That is absolutely gorgeous, Gerald, to see Europa Clipper on its way.
Yay. And I gotta say, like, for my 4th launch, that was the first launch that has had a camera where you can watch the spacecraft separate. And it really did feel like a little separation anxiety. There's your baby, like, walking across the stage. Like, you can't go touch it anymore. Like, ooh, it better work. So that was super exciting. And fortunately, there were some more exciting parts that happened during launch, but just in the interest of time, I had to choose specific things to tell you. So now I'm going to tell you a little bit about things that happened during the first several weeks of the mission that we called flight system characterization. People often ask me, so you launched a spacecraft, you've got 5.5 years to go. What are you doing? Like, are you twiddling your thumbs? Are you playing solitaire? Like, what, really? And for us, there's a lot of things we have to do in order to check out the spacecraft, check out the instruments, get ready for the big events that are gonna come. And so for the first 3 weeks, our focus was doing all the things we needed to do in order to execute our first trajectory correction maneuver. That's, you're sending the spacecraft, you know, millions, billions of miles away. You can't just throw it and expect it to, like, do all the solar system billiards. You have to fire your engines and do little course corrections to make sure you're on the right track. And so we needed to do one just 3 weeks out. So baby spacecraft, must do thing so that it is on its journey. And so to do that, we had to make sure the prop tanks were appropriately pressurized. We had to understand how our thrusters were performing. I can't find my mouse. Oh, hi. How our thrusters were performing, and also check out our star tracker, the thing that lets the spacecraft know where it is, and also something called the SATA. This is the drive electronics that hold the solar arrays to the spacecrafts. And one of the reasons that that was important is because we needed to make sure that the solar arrays would be steady in a certain position when we were doing our maneuver. And we also took some time to, like, pulse the thrusters and watch the response of the spacecraft. You see the picture of the spacecraft, it has these huge solar arrays out there, and they're stiff, but they're not that stiff. And if you're going boing, boing, we need to understand that the attitude control system could handle that. So we needed to do multiple activities through those few weeks to check all that out while a team of people were building the sequence to do the trajectory correction maneuver, running the test, looking at the data, making sure that it was all working. We were busy bees during those few weeks. And while I'm not telling you about any fun little sideways things that happened, there always are. You guys might think, you know, you're at NASA, you guys are geniuses, nothing ever goes wrong. So not true. I mean, I didn't say that the way I meant. What I meant was there's such complicated spacecraft spacecraft, and they're very hard, and there are little things that might go a little bit off kilter that are not gonna destroy the mission or even harm the mission very much, but you have to understand them. And so we had a triple handful of things that we were working during that whole period. But fortunately, the maneuver got off just fine, yay. And then the next 3 months, we had what we called Flight System Characterization 2. And our focus was major deployments. The thing I didn't mention, I talked about the solar arrays being tucked up inside the launch vehicle, and those needed to come out within the first few hours of separation. The magnetometer boom that has our cool instruments that are going to measure the magnetic field had to deploy. And these very long radar and these small ones needed to get deployed as well. So there were those other instruments that we were checking out and calibrating. 3 months sounds like a long, cushy time. We were busy bees. There were a lot of things that we were doing. I love our previous operations chief engineer described it this way. It's like a layer cake where you're flying the spacecraft, you're building the commands and products you need to do the next things that are down the road, you're dealing with any anomalies that you have, you're thinking strategically about what you have to do in the next 6 months to a year. Like there's a lot of things going on all at once on our team. It was kind of a blur of activity. And so you guys might recognize this time span. A pretty crazy thing happened here in the Pasadena, Altadena area in January, right? The fires happened right in the middle of all of that. Now, in that January, we were in the middle of a multi-day checkout for a very complex instrument. A team had flown in from Texas for it when this happened. And we knew, we saw the forecast, we knew there were gonna be high winds, and at the end of the day, we told everyone, so go home, we're gonna have a late start tomorrow, we're just all gonna remotely dial into a meeting at 10 a.m. and see if the winds had died down, and we're gonna come in around 1 o'clock, and we're just gonna get going with this activity. And we were, talking to our Texan colleagues, like, I know this seems weird, but winds are a thing around here, there's gonna be branches down and maybe power outage, we're gonna do it to be safe. And so we all went home expecting that we were gonna have a late start, but the next day was going to be normal. And that evening is when the fires broke out in the Pacific Palisades, and then later that night in Eaton Canyon. As the Eaton Canyon fire spread, people were being evacuated, homes and businesses were being lost, and JPL was completely powered off. That means no power to the Mission Control Center, and when that happens, it's like, your mouth to talk to the spacecraft, your ears to listen to the spacecraft. Your DSN stations are still working. They still gather data coming from the spacecraft, but it wasn't going anywhere. It wasn't coming here to JPL. It wasn't getting piped out to all the people who needed a JPL. So it's like we had a baby spacecraft that had launched a few months ago, and we yanked the baby monitor out of the crypt. Like, now you're on your own. And it was the right thing to do. The lab had to shut down. We were in danger. Like, it just was what it was. And I love the fact that our leadership on the project, myself included, were telling people, just do what you gotta do. Make sure you're safe, make sure your family's safe. People were evacuated. People were just worried about their friends and family. And so we shut it down, and we were staying in contact with each other via cell phone and text message and what we could do. But we also knew when we learned that the plan was we were just gonna chill out, we were gonna come back and power up the lab on Monday, we knew that for us, we had a slightly tighter deadline, because when you launch spacecraft, they have to be able to recognize when something's wrong with them and then take action. And one of those things could be, something's wrong with my radio. How would you know that? There's lots of things where if something breaks, the software can detect it and then do things. But there's also just I haven't heard from anybody for a while. I wonder if there's something wrong with my radio. Maybe I should swap radios. Well, I still haven't heard anything. Maybe I should swap amplifiers. Maybe I should swap computers. Maybe I should reboot. Maybe I should do it. And it just accelerates, right? Because we don't want a spacecraft to sit there with no communication because there's something wrong with it and it doesn't know. And so we program it this way on purpose. And it has a programmable number of days that it will sit and wait and before it tries things. But because the spacecraft was brand new, we had a programmable wait of 5 days. And when we set it in the morning, so when we went home the night before the fires, the next morning it was gonna be down to 4 days. And so when we talked to each other and did the math, we didn't do the math, we just always know when it's gonna expire. It was going to expire Sunday morning at about 8:30 a.m. I love our leadership, both at the lab and on the project. We're very professional about this. People got in touch with each other to say, so I know we're gonna open up on Monday, but and we need people to like focus on their families and all the things, but just so you know, the spacecraft is gonna start wigging out a little bit if we don't talk to it before Sunday morning. And the interesting thing about that engineering challenge is we've designed it to be safe. It's doing those things which should be safe. But also, when you have a brand new spacecraft and you're finishing up checkouts, you don't want it to start like swapping hardware and doing all sorts of things. And so we were motivated to go do something. And fortunately, the lab is full of very dedicated human beings. And so once they knew that this was a thing for us, the timeline for getting things powered up is accelerated. You cannot just like turn it on and expect it to be fine like we can do with our computer. This stuff hadn't been powered off for years and years, guys. So we had to power on things, do checkouts to make sure it's working, power on the computers in our mission support area, do checkouts to make sure it's working, think about should we send a test command, what if something is not working right? So it was a little bit of an effort, but ultimately we were able to get the command sent in on Friday with lots of time to spare and kept Clipper from having separation anxiety for us. Crazy. And then you guys all know, many of you are living it today, the aftermath of the fire. I wish I'd found a picture of the Pacific Palisades because we have friends and colleagues who live there too. But you can see how close the burned area got to the lab. Lots and lots of people that we know and love lost their homes, lost their businesses. Even for people who didn't lose their homes and had to deal with remediation, are still outside of their homes. Like, we all know that we're going to be in recovery mode for a very long time. The other thing that I'd like to say about this, I'll say some things about people later, but for me, it was beautiful to see how the community banded together over this. People reached out to help each other, invited people to stay at their homes, just come over for a shower if you don't have water. Lots of GoFundMe pages where we were just trying to do everything we could to help our own community and also the communities that are out there. And I know it's going to be a long road. It's going to take years for the communities to recover. So January was a month. And then we kept going with Europa Clipper. And as you saw, we needed to fly by Mars in order to get a boost from a gravity assist to continue on our trek to get all the way out to Jupiter. There was a just gigantic amount of work in order to get this done. You saw some of the things I talked about that we were doing to lead up to launch, some of the things that I talked about, very busy flight system characterization, and a core team of people who had been keeping our focus on getting ready for Mars. Some of the most important things for Mars was doing the targeting maneuvers and aiming ourselves up so that once we got there, we would be on the right glide path, the right trajectory, the right angle, the right altitude, and everything in order to get it. We also turned on 2 of our instruments to do a calibration and a functional checkout. Our imager, the e-Themis imager, that is kind of infrared that lets you see hot spots on the surface, did some really cool imaging of Mars for a calibration. So we captured Mars in the infrared, and that allows the scientists to understand that the instrument is working and do a little bit of cross-science with other orbiters that are there at Mars too. The radar did some pings, just like it's going to do pings when it gets out to Europa. I do not have a pretty picture to show you of that one, sorry. But very exciting that we had that opportunity to check out instruments. So what is next for us in the near term? You saw we went past launch, we went past Mars. There's any number of things that the team is still doing, from instrument checkouts and calibrations. The biggest thing for us is the flight software update. And I wish I had really cool, I should have asked AI to make me, what is a cool flight software update? So you get a purple spot. That's going to happen in August. And there's just an enormous amount of work underneath that purple splat about what's going on. When we get spacecraft ready to go, especially spacecraft that are going to a new place, that have new instruments, that have a new way of operating, we have to write a lot of unique flight software. And for anybody who even just loads an app on your phone and is trying to do things with it and realize that it isn't working and you need to wait for the next update, that's kind of one of the things we had to deal with. And before launch, we focused on those things that were necessary for the spacecraft to be able to successfully separate from the launch vehicle, deploy its solar arrays, do all the checkout things, do the maneuvers, and the things that were necessary for deeper cruise or necessary for tour, we were like, and we'll do that later. So there was a large team of people behind all the operations team working on those fixes and testing them and ensuring that they were doing what we needed them to do so that we can get ready to do a software update in August, which will seem like a long way away from launch, but trust me, for me and the people who have been working on it all this time, it still feels pretty close in. It's almost like you're driving your car and you would like to do a software update of your car while you're on the road with it. It wouldn't feel super safe, so there's some things we have to do in order to ensure that that's done well, and then we have addressed a lot of those little issues that we couldn't get to prior to launch. And then we'll continue on our way. Please check back with us after the Earth flyby. We'll have a lot of interesting things to tell you then about how the spacecraft is doing. And then we'll be in what I'm gonna tempt the universe by calling quiet cruise for a while until we get closer, and then we'll be doing a JOI demo about a year out from Jupiter, et cetera, et cetera. But the reason I hesitate to say quiet cruise, on Juno, we had a 5-year cruise to get all the way out to Jupiter. First, we did launch, and then a year later, we did some deep space maneuvers, and a year later, we flew by the Earth, and there was gonna be 3 years of quiet cruise. So many things happened during quiet cruise that we got a piggy bank, and we told everyone on the team, if those words come out of your mouth, stick $1 in the bank, and we're gonna have a pizza party. So I suspect it's gonna be that way on this mission too. We'll see how that goes. And there we go. So I'm not actually gonna tell you about all the things in detail that are gonna happen at the science show. You're just gonna have to invite me back or invite someone else back to tell you all those things. So my last things, you've heard me talk about people and teams and heroics. This picture is a couple of years old. I know we recently took a new one. I can't wait to get my hands on it to stick it out there, but it really does take a village to do missions like that. The number of people who've worked on this mission is enormous. Around launch time, there were about 650 combined between JPL and our partner APL, Applied Physics Science, and about 220 scientists at various institutions, so maybe like 1,000 people across the country. And over the lifetime of the mission, somewhere upwards of 4,000 people have been involved in this mission. And if you add in our subcontractors, that's probably many thousands of people. And these are people who are not just what you'd expect, that are really smart, really dedicated, really hardworking. The number of hours some of our people worked over many years is like staggering. It's just lots of dedication and commitment to deal with not just the nominal design and development and the nominal things you would expect, but also all of those curveballs that the hardware and software in the universe threw at people. But they're also funny, like hilarious. It's really fun to hang out with them, and sweet and kind and nurturing and heartwarming. And this group of people is, like, the science is cool, don't get me wrong. The engineering is awesome, yay, that's why I signed up to do this. But coming to work and getting to work with people like this every day is really the thing that motivates me and gets me up out of bed every day. And so I wanna say, I know there's lots of Europans in the audience. If we can have the house lights up, and if you guys can just stand up for me. Don't be shy, I know you're out there. If you've worked on Europa now, if you've worked on Europa in the past, engineering, science, outreach, all the things, business people, like, do your thing. Just, yes, warm round of applause for all of you. Like, you guys, and the ones that may get to watch this later because they're still in the NSA working right now, you guys are the ones who do all the work. And I just get to be up here talking about it and sharing it with everybody, which I'm thrilled to do. I'm glad that you guys came and love that we got to talk about Europa Clipper. So that's it. Now Q&A.
All right, it's your turn. Get those questions ready. Tracy, you embody this mission quite literally, and it was just a joy to watch you describing the motions of the spacecraft and really see how intimately involved you were with exactly what's going on in space. It's wonderful. Have you always found like that level of emotional connection with your work as an engineer?
Yeah, I think so. I'm a person who talks with my hands, and I'm a people person. I'm in touch with my inner child. You saw the picture up there. Yeah. And I think that just because you are an engineer or a scientist doesn't mean you have to be all like straight-faced all the time. And it feels like you are alive, like a living person doing this work instead of just a robot.
I like to say scientists are people too.
Exactly.
And then I have another question from my friend Audrey, who should be probably entering grad school about the time that your science tour starts. She wants to know, is it coming back?
Is it coming back? It would be nice. We miss our little baby spacecraft when we send them out there. But unfortunately, no. There is not enough fuel in order for it to break away from the gravity of Jupiter and come all the way back. So Clipper will stay there and do its mission. And then when we get near the end of the mission, we will deorbit it. Either into Jupiter was our original plan, but I think we have permission now to deorbit into Ganymede, which is also a really cool place. Space litter, not good, but the ice around Ganymede is very, 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 very thick. And so they don't think that there is an environment for life that we could unintentionally contaminate, like we could if we lost control of the spacecraft and were to have an unintended deorbit onto Europa. So that's why you have to dispose of the spacecraft at some point near the end of its life.
Okay, we have significant number of questions, so I'll do my best.
We can do speed round, like the last 5 minutes can be speed rounds, right?
You might have to, actually. The first one I want to ask is, obviously, the effort that goes into making sure that this happens at all is immense. Yeah. Tell me a little bit about some of the decision-making points where, you obviously want to maximize the science and some of the other trade-offs that have to be made to make sure that all the instruments that got on board get their moment in the sun, so to speak.
Yeah, that's always challenging. The interesting thing for me, joining the mission relatively late, just 6 months before the critical design review, some of those hard choices had been made early on. We had a different magnetometer earlier on, and they needed to change it out for reasons that made us able to meet our schedule and budget milestones. The reason antenna, speaking of reason, anyone who's familiar with solar arrays that produce electricity, so they have electric fields through them, radars that can be sensitive to those kinds of things are like, really? A radar on a solar array? What were you thinking about that? And it's just, they're so large that it was challenging for the team to find a place to attach them to the spacecraft that would work. And believe it or not, with all the trades that they did, remember the wedding planning and the seating, that turned out to be the option that was the most viable. So there were lots of things like that people had to think through.
Yeah, so I guess part of that trade-off is how much science you can do, but then also how much information you can actually get back from the science that you're doing, right? Because
that's right.
You need to actually, I would assume, analyze the data.
Yeah, you
right?
kind of need to get it back, or why did you go? Reason is one of our data hogs. You just need a lot of data in order to be able to decode what the radar is finding. And so one of the trades is for all the different instruments, who is allocated how much space on board our data storage system, and when does it come down, and how is it prioritized? So there's lots of people who spent a lot of time thinking about that.
All right, I have a very specific trade-off question for you that I'm going to have to read verbatim.
Okay.
What were some of the key decision points when the decision was made for MEGA versus Hohmann transfer for the Clipper Europa mission? And can you explain what that question means to me?
Nerdy people out here. So I should have said MEGA because it's such a cool acronym. We love acronyms. So MEGA is Mars Earth Gravity Assist. So the fact that we have to fly by Mars and then the Earth to do our gravity assist to get all the way there is the MEGA trajectory. Right now, the phase we're in, it's called Epic Earth Point Intercruise. Epic! That's what And then the direct trajectory is if you didn't have to do that pool ball game, and if you could just go straight on a curved orbit, that's the Hohmann transfer orbit, all the way out to Jupiter. And in order to do that, you have to have a powerful launch vehicle that can give you enough energy to get out of the Earth's gravity well and going far enough to get out there. And so for a long time, the project was maintaining an ability to fly on either a Falcon Heavy, which didn't have enough energy to do that, hence the MEGA trajectory, or a Space Launch System, the new NASA launch vehicle, which did. We could have straight shot 2.5 years. That would have been great, but unfortunately, schedules being what they are, it didn't line up for us. The stars did not align, and so we needed to launch on the Falcon Heavy and do the MEGA trajectory. So it really came down to the launch vehicle. We stayed compatible with both for a very long time, hoping it would come through, but it didn't, so MEGA it is.
It's okay. You're on your way there anyway.
We're on our way. We're doing it. And we're past the M, so now it's just EGA.
If Clipper finds signatures of life and subsequent missions confirm it, what will it mean to you as a person and as a scientist, Tracy?
So I'm going to channel my inner Bob Papalardo. Like, we are not looking for signs of life. We are looking for signs that Europa could be habitable for life. A subtle difference, but it matters to what our objectives are. And so I'm going to adjust the question a little bit. If Clipper finds that that is true, and later missions confirm that there is life down in there, like, would it be great to have some way to dig underneath the ice, not contaminate the ocean down there, and discover things? For me personally, Tracy Drain, not representing NASA right now. For me personally, I think it would just be amazing to have potential evidence that life could start somewhere else. I mean, there's the idea that there were like comets that landed here and everywhere, and that it could have been like multiple, like single source that still kind of germinated things on the planet. But I personally, as an engineer, not a scientist, ascribe to the theory that Earth kind of gave birth to life here. And so if there's evidence of life on Europa, I would be wondering if life spontaneously evolved there too, and could be very different from what we see here, or have similarities because the ingredients are all similar, right? So it would be cool and like open a whole chamber of what ifs and what ifs mean.
Oh, as a biologist, I'm totally right there with you.
Yeah, I would call you, hey, guess what?
Is there, speaking of sort of what things mean to you, is there a through line of purpose or interest or passion that you've sort of followed? I mean, you've mentioned more than just this mission that you've worked on. What's driving you as a person and as a leader?
Yeah, for me, it's evolved over time. I have been working at the lab for 25 years now. See my little Grace? And for me, my initial impetus was, science is cool, space is cool, engineering is fun. It was getting to go to work and play all day. Lots of stressful play. But
That's the dream.
That's the dream. And the fact that we are adding to human knowledge about the solar system and the universe that we live in was that was all of it. But then the more, and I've always been a people person underneath that, and systems engineering as a discipline is one that drives, like, your job is to talk to people doing different things and make sure it's all gonna work together. And for me, it's become more and more about the people and how we're doing things, and that we're doing things together. And as a leader, when I got the opportunity to help people figure out how to be better at their job, help people figure out how to stay sane while doing their job, help people figure out how to work better together so that we could accomplish more as a team, that felt like a pretty significant accomplishment, and also just a great thing to be doing as a human.
How do you define your sort of leadership philosophy?
My leadership philosophy, I should have a good answer to this question. I have 5 young professionals that I mentor. I'm gonna call each of them, like, given what I've said to you, what do you think my leadership philosophy is? I think for me, it is, this job requires so much creativity, and the kinds of things we do are so challenging, no one person has the answer. I can't say, this is the answer, like, you get a D, like, you go to it again. It is, how do I nurture their creativity, give them space to think, point them in directions, but not put too many guardrails in place so that people can stretch their own minds and come up with solutions that I wouldn't have been able to come up with myself. And a lot of my leadership style consists of a lot of listening. I want to hear the thoughts and ideas of people and then figure out how to integrate them together. If I hear something that I think doesn't work, my response is not, that will never work. My response is, okay, I'm concerned about this. Can you tell me how your idea would address this concern? Because they might have thought of it and they might have come up with something. So it's a very kind of lead this way instead of a like run in front with a flag kind of leadership style. And that works well for a lot of people. I think that can be challenging for a lot of people who are like, could you get out there with the flag, please? Like, where are we going? So it's interesting to also work with people to feel out what they need and how your style might not fit and how you can adjust to be the leader that they need to.
Yeah, you have to be confident enough to listen
as
well.
That's right.
Not everyone is. Okay, back to space. So do you expect many more missions like Europa Clipper investigating other moons and dwarf planets with subsurface oceans? And what's coming? What can we look forward to?
I can say I hope for many missions doing those things, especially because when we think on a short time scale, we can be a little bit, we can have blinders on, a little myopic about what's possible. But I grew up on science fiction, and so I think, well, in 50 years, 100 years, and 10,000 years, right, if we are going to be a spacefaring species, then of course those are things we'll have to do. It's just a matter of how long we will be around to see some of it, and whether some of it will happen after we're not here anymore. And so I think that the idea of having outposts on other moons where there are resources that can help you thrive, and hopefully in a way that is learning from some of the hard lessons we've had here on Earth, so that when we go out farther, we are being sustainable and we are not creating, damage to where we're going, that we look more like caretakers out in our solar system and our universe instead of like locusts, right? Ideally, that's what we would do if I could rule the world. Yeah.
Interesting.
Yeah, thank you for that. Come with me to do that.
Sounds like you might have some votes.
Yeah.
And speaking of kind of preparing us for the future, there's a question here about why solar instead of nuclear power?
That was a decision that was made before I joined the mission, but I know when we think about missions that are going very far away, we always have to do that trade. It's the wedding party all over again. Does it make sense to do solar, or does it make sense to do nuclear? And both of them have their pros and cons. One thing that's nice about solar is we have flown many solar missions that has a lot of heritage. You don't have to deal with as toxic chemicals, so it's less hazardous when you're doing things on the ground. You saw Juno solar mission. Juno was the first solar mission to do solar at Jupiter distances. Go Juno! And solar arrays continue getting more and more efficient, so we just know that it's possible. Nuclear is great because you don't have to worry about so many moving parts. You don't have to worry about things getting stuck, or like the whole thing in the solar system, we got to point the arrays, but not too much. You don't have to do that as much with nuclear, and so it has its pros. But also, there's less nuclear fuel around, and then you have to go through so much more additional launch approval hoops to make sure it's all safe. So you just picked the one that's right for your mission, and solar was right for Clipper.
Was there anything that NASA and JPL did that was considered new or innovative in creating Clipper? And can you compare it to previous spacecrafts? Like you already started, so.
Yeah, let's see. Are there things that I have not told you about that were new and innovative? I mean, the instrument suite itself, there are often things that are, heritage back, like our ultraviolet spectrometer is very similar to the one that we've done before. But there are also things that are new to me. Ooh, this is where I'm going to get in trouble with my scientists. Which ones are very new? I know that Reason has heritage for other long radars, but we haven't done radar at Europa Clipper before, or at Europa before. So that challenge in having huge amounts of data and sending them all the way back. Our bulk data storage system that we have on board, it was a pretty new development. Yeah, there are multiple things. I'm going to write that one down as a question I'll study for better later next time.
I have a feeling that this particular question is helping to settle a bet. So what programming languages do you use on board the spacecraft? It's just as, I know you people.
That is hilarious. Should I just not tell you? Would that be fine?
Someone's got money on this.
I think. Well, do I even know the answer? Me, systems engineer, not programmer. Where's Vince? Vince, I know you're here. Where did you go?
Okay, so see him,
Vince,
if that was your question.
What is the programming language that we use? Why don't I know? VX works? What is it? We use C. Thank you. C, that's Vince Wu, flight software developer. C. I grew up on Fortran 77 myself. Ha!
And the last question, and I also want the answer to this because I remember when the mission was named and there was some question about why JPL wanted Clipper when we had Dragon and Falcon and so much more like aggressive and grandiose names that were coming out, and then it was Clipper. So why Clipper?
Let me see if I remember this. I learned this from our project manager a couple of years ago, so my memory is going a little bit fuzzy. So a Clipper is a type of exploration vessel back in the day, and I think the thing, it had these huge sails. Some of the old designs of our mission shirts had like these big masts with lots of sails on them, and it could move very quickly. And I think the thing about Clipper is that it could like go close to shores in order to fight the trade winds. And we are going to be like going close to Europa Clipper and doing that multiple times, kind of like a Clipper ship. I think that's the story. Did I get that right? Any Clipperites in here who like know? Do you want to? I see some head nods. Thumbs up. Yay, thank you. Okay.
I guess that just goes to show that history repeats itself.
It does.
Well, thank you so much for sharing about the mission, and we look forward to having you back after Science Tour.
Thank you.